Hello everyone. I hope you can hear me.
Yeah, sir, you're audible.
Okay. Thanks, Abhinandan. So in week two, this is the first week in which we are taking a deeper dive into machine learning techniques, and a technique that sir is going to introduce is this one is linear regression. And the linear regression has two parts. We will be covering linear regression for week two and week three. In week two, there will be introduction, and week three, there will be regularization and polynomial transformation. So in week two, Sir has taken this linear regression technique and covered its 5 components, which are data set, how the data looks like, what are the properties of it, what should be the target variable nature. Second is what is the model, how does it look like, and can we visualize it. Third one is the loss function. What kind of loss function do we use for choosing the best model? The next one is even if we have the loss function, how do we use that loss function to actually guide us through the best or optimal solution? And the last component is evaluation. So after we have optimized our model, we come up with a candidate good model. Then how do we gauge its accuracy or how good that model is? We do that in evaluation step. So before we proceed, anybody would like to share comments or any experiences in week two? Okay. So let's begin. So let's go to first activity question, which is the output level in a regression problem is. So what it looks like. So there are 4 options. Let's go to one by one. Discrete and integer, they look dubious, but not clear winner. Irrational is definitely not the answer. Real numbers is definitely the one, because in regression the output variable can have decimal values, and it can range from well, for depending upon the problems, it can range from minus infinity to plus infinity, and it can have decimal numbers. So real is the best answer for this one. Let's go for the second question. So Swarnim is a Virat Kohli fan. He wants to predict the runs Virat Kohli will score on the next time he bats in a cricket match based on the runs scored by him in previous 100 matches. This problem can be classified as. Okay. So see what is given in the question. So first thing that is being given is that he wants to capture or predict the number of runs Virat Kohli is going to score in the next match. Okay, so that's a prediction problem. And how do we predict, what data do we have for training our model? So that is also given in the question, that we have a record for past 100 matches in which Virat Kohli is batted. Okay, so we have this training data, and this is the problem that we want to solve. We want to predict the number of runs Virat Kohli is going to score in next match. And since, again, we have to decide which type of problem is this. So we have to look at the target variable, which is the number of runs. So you can quickly guess that it is definitely not discrete, classification problem. Like we have, for example, if you take an image and figure out whether it's cat or dog or something like that, that is definitely not there. So the number of runs Virat Kohli can score could be from 0 to 100 or maybe 200. Okay, so that's why this problem will fall into regression problem. Let's look at the other options. Classification, definitely not. Dimensionality reduction, no. We are not given any information about the features, so this is out of question. Density estimation problem is also not the right answer. The only answer which is relevant is a regression problem.
Sir, I have a doubt here.
Sure. Yes, Shreya.
So for every supervised learning problem, is it correct to say that it has to have inputs of features and labels both?
Exactly. You're absolutely right.
Okay, so in this case, what are the inputs and what are the labels? Like, I understand the labels would be the runs code, but what would be the input or the features here?
Okay, so the input of there could be so this could have a different type of features. For example, Virat Kohli, let's say he batted in Chinnaswamy Stadium,
Okay.
maybe against South Africa, and he scored 30 runs. Okay, before
Okay.
that he batted in Mohali on this and that date and against West Indies, and he scored, let's say, 40 runs, something like that. So we can have records like this. We can have even fine-grained records like in the Chinnaswamy match, he batted against South Africa, and let's say against Rabada, he scored 10 runs, and there was another bowler on against who he scored 10 runs, and so on. We can have finer details also. So this will form a single sample. So this is how we can have features.
Okay, got it. So my doubt is like, then if there are no features,
Mhm.
can this also be an unsupervised problem? Like if we are trying to predict without any features?
So if we are trying to predict without any features, and all we have is, let's say, the number of runs he scored in previous 10 matches.
Yeah, yeah.
Okay, so it is like then it becomes a tricky problem to solve, because we don't have so next match. So let's say so if I understand your question correctly, if there are no features, how can we solve this? Is it?
Yeah, then is there a possibility that we solve it in an like it becomes an unsupervised problem? Like in this case, because there were no features, like nothing was mentioned, I got confused that it's a regression problem. That's why.
I see. So uh, I think it is still going to be a supervised problem.
Okay.
I mean, it is still supervised problem because we are predicting exactly one quantity, which is number of runs.
Okay, so we can still have something like a time period or something like that. Maybe
Yes.
suppose we are taking weather prediction or something, we can have time as against the actual temperature and something like that.
Yes.
Okay,
Exactly.
got it. Okay, thank you, sir.
Yeah. Okay, let's move on to next question. Output of a single label regression problem is okay. Now this is so this is similar to let's take again the example of predicting the number of runs Virat Kohli is going to score in next match. So what it is going to be, since we will have a single quantity, vector is out of question, because vector is a collection of more than one quantities, scalar quantities. Tensor is also kind of vector for now. Let's not go deeper into this, but that is also out of question. The only thing which remains is a scalar. So a scalar could take value from 0 to any positive number, which is the range of number of runs Virat Kohli can score. So it fits this example. And if we take in general for any regression problem, the single label regression problem, the output could be from minus infinity to infinity, and therefore it is a type of scalar.
So, but it's a scalar,
Yes.
assuming we are talking about only one input, right?
One target variable.
One input sample also, right? If there are multiple input samples, then we are talking about a vector, correct?
If we are talking about multiple samples, then the output multiple scalars, right? But the intent of this question is, I think, output of a single label regression problems. So, so for this one, okay, I understand your doubt now. The focus is on what is the type of the label for a single
itself. Yeah.
Yes, output itself.
Okay, fine.
Okay. All right. So let's move on to the second part. Okay. So this is about the model in regression. All right. So this is an interesting one. Now things will get more interesting. If a regression model contains only one feature in the input data and one output label, then the model can be represented by Okay, fantastic. So what we have is only one feature, which is, let's say we have x-axis. There's only one feature. So we can imagine, maybe if I imagine things, that will contain an answer. So, but still, let's do that. Let me share my screen. Is my screen visible, this whiteboard?
Yes, sir. Yes.
Yes.
Okay. So let's imagine we have this x-axis and there's this y-axis. We have only single feature. So since if we have only single feature, we need only one axis to represent it. And y could be anything. It could be something like this. It could be something like this. Anything is possible. Okay. So this is our label, and this is our single feature. Now, if we are talking about linear regression, what we have to think about is one weight is definitely going to go for which is the x. Okay, there will be one quantity, and there will be one more term for bias. Am I right?
Yes.
Yes, sir.
Yes.
Right. So, if you have gone through the videos, sir represents this with, this is W1 and this is W0. So this is like saying, this is one representation of the model, which is equivalent to y is equal to mx plus c. And can anyone tell me what kind of equation is this?
Line equation.
Line.
Exactly.
Linear.
This should be a line. So if we let's go back to our website. Okay, so now, of course, line is the right answer, but let's consider for a minute what are the other options there. Circle is definitely not an answer. There is a single feature, and circle requires square of a feature, so that is definitely out of question. 2D plane, option 2 and option 4, both of them represent 2D plane in 3D space or 2D plane in 4D space. So we are going to get a line, single line. So these are also out of question. These are also wrong answer. The correct answer is line. Okay, let's go for the next one. For a regression problem having m features, the weight parameter vector has following shape. Okay, so now the problem has increased its dimensions. All right, so let's, okay.
Plus 1 by 1.
Exactly, that is actually right answer. So this time, instead of having just one feature, which was earlier there, now what we have is we have m number of features. So there x1, x2, x3 up to xm. Okay, and since we are talking about linear regression model, for every feature we are going to get a single weight, w1, maybe I should w1 plus w2 plus w3, and for every feature we are going to get a weight wm. In addition to that, we are going to get a bias term. Okay, so if we count all of this, this has m number of items plus this one, so 1. So total we have m plus 1 number of parameters. So the correct answer should be m plus 1 by 1. The other options, m minus 1, definitely this cannot be, okay, give me one moment. So other options are m minus 1, which is definitely not going to happen because we will have lesser number of parameter vectors as compared to the number of features. So this is out of question. The 2m multiplied by 1, we don't need additional m number of parameters. So what we will be multiplying it with? So that's why this is also wrong. M plus 1 and M plus 1, these two, A and B, are the closest possible answers. So for the explanation that we just saw, I think M plus 1 is the right one. Any questions? All right, let's move on to the next question. The model representing relationship between features and the output label is unique. So, so this is, let's go again. Right. So let's say we have a set of points. I hope this drawing is visible.
Yes, sir.
Okay. Okay. So this is the data points, and let's say we have a model like this. So this is a model. Okay, this is the trained model. For example, assume that this is the model we have, and we could also possibly have a different model which could look something like this, the pink one. So this is model B, this is model A, and we can have one more model. Let's say we have model C. So you can see that, you know, all three of them, they are quite close to each other. Of course, if we just visually inspect and want to figure out which is the best one, we will say A is the best model. But A, B, and C, all three try to represent the relationship between data points and the output label. So for any data set, there could be infinitely many possible models, candidate models. So even I can draw even some of them which are even worse than these. Let's take, so there could be one like this. There could be one like this. They are all not good. They are bad models, but they all of them try to attempt the relationship between data input feature set and the label. So the intent of this question is it possible? I mean, is it possible that there is only one unique relationship between data set input features and label? The answer is, of course, no. Okay. Any questions? So this one, I think this is an important point to understand. Even through the optimization procedure, when we are optimizing our model, we update our weight vector. So as soon as we update our weight vector, we get a different model, right? Which is better than the previous version. In the next iteration, we update our weight vector even one more time, and we get an even better model, which is closer to the first two models that we got. So the model representing relationship between features and output label is unique. That is going to be false.
So on the portal, I think it's given as true.
True, yeah.
Oh, let me check.
I think the question, the original intended question was that if you have a trained model and if the loss function is d squares, then is this true? In
Yes,
that
yes,
case,
of course.
then it will be unique, but otherwise there will be infinitely many models.
If the loss function, okay, so you know, there is a possibility that we could have multiple optimal solutions. I mean, it's a tricky concept. So for example, for the loss function that we
The
are taking
loss
this,
function is multiple minima, global minima.
yes, yes, yes.
But that cannot happen if your loss is squared, is a quadratic loss, right?
Right. So that is true. The best model, or you know, for set of parameters and set of features, the best model with this loss function is going to be unique, of course, given that we have run it sufficiently longer for sufficiently large number of iterations.
Right.
But in general, you know, there could be many models which could
Models.
represent possible relationship.
The only way that this is true is if we add those two assumptions also.
Right. Yes.
Okay, that the model is trained and the loss is your standard regression loss.
Yeah. So yeah, the one beauty of that summer squared loss or mean squared losses, that it has a unique minima.
So, sir, is it possible, like, say, for example, you have a loss, say, for example, loss is 2, okay.
Okay.
So, for that particular loss, your W0, W1 can be different.
It is,
Different
I
in the
think,
sense,
yeah. It is definitely possible. Absolutely
yeah.
possible.
So W0, W1 is no way like I can say whatever W0, W1 I got is unique W0, W1, right?
Unless it is a minima.
Unless it is a minima, yeah.
Yes, yes. Yes, Rajiv.
Okay.
That's right.
So it should also be linear, right? Like it should be, that's another condition.
The model is supposed to be linear, is it?
No, I'm saying like only then it's unique, because I can have linear and polynomial model for the same data set, right? Which again
Right.
doesn't make it unique.
Right, of course.
But sir, when we are telling about a model, okay, model means nothing but a function, right? So when we
Yes.
then what feature you are passing, and you will get the output always will be unique, right? You cannot have a function where you are putting a different value and you will get the output same, right?
Right. Yeah.
So in this case, the model representing should be unique.
A model presenting should be
unique.
No, that is subjected to fixed set of parameters. Like if the parameters are same, whatever X you will get a like a unique Y.
No, but once your model is ready, how the parameter will be different?
No, parameter will be same. Yeah.
Then we are talking about the model representing. We are not talking about that it is going to be trained. It's a model is then your Y, whatever Y, MX plus C cannot be different.
So so let me start from the beginning. Rajiv asked this question: can we have same loss but different models for exactly that same loss? Right? Is that right?
Yes.
So let me show you an illustration. Maybe that should help. Give me one moment. I hope that you have gone through and interacted with this applet. Did you get a chance to do so?
No, like did you send the URL somehow? Like where should we get this URL?
So it is in the slides that we shared.
Okay.
Slide is there, picture I tried. No, it's there only. The photo is there. It's image only.
Okay, give me one moment. For some reason, it is not showing properly. Give me one moment. Okay, so do you see this graph now?
Yes.
Yeah.
Okay, so on the left hand side is the visualization of the loss function. So the green surface is actually the loss function that we are that we have for this particular set of data set. And the yellow dot, can you see this one? This small yellow dot?
Yes.
Yes, that represents a single weight vector on this loss surface. So this point is actually the weight vector, which is W0 and W1. Okay, so now Rajiv's question was, can we have same loss but different models? That is possible. So let me show contours. So do you see these circles? So for every point on a single circle, let's say if you take the top circle, and every point on that circle is going to represent a model, but the loss is going to be exactly same. Why? Because it is has the same distance, vertical distance from the minima.
Correct.
Right?
Yes.
Okay, so if you did not get this link, let me paste it right now. You can also have this from the slides. I shared it in the chat box also. So we got a little deeper right away, but that's okay. So since we have this one open, let's try to interact with this one. So if I pick this yellow point and move around it on the loss surface, you can see that, as if I pick the yellow point, which is our weight vector, if I get it to closer to the minima, my model on the right hand side is actually getting closer and closer to my data. But if I pick it and move it away from the minima, you can see that, it is going away from my data points. And the farther away I go, the farther the model goes.
Sir, can you move the yellow point along a single contour and see how the line changes?
Single contour, either W0 or W1, is that? Oh,
No, just
the
like
single.
you see that one contour, just rotate it along that one contour and see what happens to the line. Because
Okay.
The way I see it, it's one axis is M and the other axis is C. You change
Right,
them,
right.
you'll get a rotating and shifting line, right? Now,
Yes, yes.
what are two
Yes.
possible positions which produce the same loss? That is obvious. Like in this case of the scatter plot we have, if there is a line which is exactly parallel to it, but say K units below and K units above, these are two models that will produce exactly the same loss.
Okay, so in order to produce the same loss, so can you see the circle, which is a red circle?
Yes.
So this is an example that for any point along this circle, you will have exactly same loss, but the models will be different.
Correct. Can you just move that point to something else on the red contour?
Sure. Maybe something like this.
Okay.
So the surface is slightly cut off since I zoomed in. Let me zoom out and then run it. Okay.
Right. Got it.
All right. So on the model side, it might not look that explainable, but from the left hand,
the geometry is not very apparent along the same contour. But okay,
yes,
if we actually calculate the loss, it will turn out to be the same.
Yes. Right.
Like for example, if I take a mirror image of this particular line across the y-axis, it will produce the exact same loss.
Along the y-axis. Okay. Yeah. That's right. Absolutely right. No, actually, no. That is not going to do the same thing, right?
Yeah,
So
not necessarily.
Sorry.
Yeah.
But if okay, clearly there is no pattern here.
Yeah, because your W0, W1 is changing.
Right.
Yeah.
And if we flip this model that we have currently on the right hand side along y-axis, then if we draw this and try to figure that out, no, the loss functions loss value will not be shown.
Then you will go to a different contour actually.
Yes, right. Okay. Now let's move back to our activity questions. All right, there we are.
Then, sir, for that question, like the answer should be false, right?
Answer should be false. I totally agree with you. Yes. Oh, I'll have it corrected.
Okay.
All right, let's move on to the next question. Which of the following, so this is all about loss function. Which of the following cannot be used for loss function in linear regression? Okay. So basically, we have to point out the functions which are not suitable as a loss for linear regression problem. Okay, so let's go through them one by one. So sum of squared error, it is definitely a usable option because that's what Sir has used in the lectures also. Mean squared error is another form of sum of squared error. So sum of squared error multiplied by 1 by number of samples will give you mean squared error. So I think that is also acceptable. The next one, the last two ones are log loss, and the first one, which is the mean absolute error. So mean absolute error, it definitely calculates a loss value or error value. It's slightly different to optimize. It is not optimized through gradient descent. Some other algorithms are used, but it is also a valid loss function. The only thing which is remaining is the log loss function, and it is typically used for a classification. So this should be the right answer.
So sir, now the question is like why log loss
Even
function
for-
cannot be used as a error for regression? It is also a monotonically increasing function, so you will get a minima.
See, so log loss function is the expression for that. If you work out on that, it will be different for this one, right? So see, yeah, Rajiv. So let's not go into detail of this as of now, because that will be covered in great detail when the classification comes in.
Okay,
So
okay.
yeah, you can read up on this one log loss function offline and see if that works or not.
So, but even absolute error is not differentiable, right?
Mean absolute error, yeah, it is not differentiable, definitely. Therefore, we cannot use gradient descent algorithm to optimize it. There are different techniques for it.
Okay.
Yeah, but still, it is a valid option. We are going to use a Lasso, regularization, and you will see that mean absolute error is still somehow optimizable.
This is a
That will be covered in
classification
lecture.
versus regression kind of a question. It's not a pick the correct loss kind of a question, it seems.
Right. So it's
The only hint here is
like,
that 3 are regression losses, 1 is a classification loss. Not
yes,
that you are assuming gradient descent.
yes. Okay, let's go to the next one. A linear regression model is basically a line on a loss surface, a plane tangent to the loss surface, a parabolic surface, a point on the loss surface. I think this should be clear by now, as we have already discussed and have seen the interactive applet. Anybody would like to take a guess?
Last one.
The last one, right?
Yeah, point.
Right, absolutely. Okay, next question is the correct expression for loss function used in single label linear regression is? So
The first
which one? The first one. Okay, the first two, they are quite close. The only difference is the multiplication of 1 by 2. Sir has used the first one. Yes, that is the right answer. The third one is definitely not going to be right answer because in the first term there is xw plus y. It is not possible. We never add predicted and actual labels. So that is not going to happen. The last one,
dimension mismatch.
yeah, dimensions mismatch, right? The first one is the only right one. Okay, next question is for a given set of training data, loss function depends upon parameter vector, feature vector, output vector, or none of the above.
Parameter.
Parameter vector, right? So output vector has no role in. Pardon me.
How is sorry, please. I think that was my question. Go ahead.
Okay. Yeah. So your question is why output vector is not there, right?
Yeah.
So for any particular data set, we take feature vector and output vector as constants. So for that particular problem, they are not going to change. The only thing which is changing is the parameter vector.
Understood.
Okay, and that is why we only optimize parameter vector during optimization procedure. We assume that feature set and the output, they are constant. All right. Okay, let's move on to the next part. Okay, so this one, I think it is not properly written. It should not be this, it should be something else. Let me share my screen. Is it visible?
Yes, sir.
Right. So the correct answer should be, if it is dw transpose of x divided by dw, the answer should be
X.
right, only x. So this one, I think there has been some queries about this one in discourse also. So let me expand this particular one. So w is a vector. So what we have is values from w0, w1 up to, let's say, wm, and x also is a matrix since it is capital X. So there will be x1, x2, x3 up to xn. There are xm, and this all belongs to one sample. Similarly, there will be nth sample in which there will be all these features. Right? So size of this will be n by n. So the first thing that comes into mind is how we can actually differentiate a vector with respect to another vector. So let me do it this way. Let me clear all of this. So let's say if I have a function which is f of x, x1, okay, maybe not x1, w0, w1, w2 up to wm. I have a function like this, and what I want to do is I want to find out the partial derivative of this function with respect to each individual feature, or sorry, the parameter. So what I can do is I can write this by this, then again I'll write f and w1, and every time I'm going to differentiate it, this function f, but with different parameter. All of this I can concisely write as something like this. Instead of writing m number of equations, I can write just single quantity. So this is a concise representation of writing this.
Sir, the bottom one will be del W, right?
Yes. So it should be something like this, right?
No. That del FW, del function of FW by del W. You have
So
written
there,
both del FW.
On the
right?
right hand side.
On the right hand side, yeah.
The last equation. Last
thank you.
equation.
Yes, it should be right. That is wrong. It should be this. Okay, so is this clear? How do we differentiate and write these vector partial derivatives?
Yes, sir.
Okay. So this one is incorrectly written. It should be weight vector W and capital X, and then these answers should be there. I think the intention was something like this. If we did, and the derivative should be also with respect to W, then I think the answer should be X. So that was the intention, but it has been mistyped. Similarly for this one, we can expand this and get the answer 2xw. Is this one clear? Because this is slightly complicated than the previous one.
Yes.
Okay. Would you like me to, anybody would like me to expand on this, how to solve this?
Not really, but there is a shortcut. Like if you see something like, let's say W transpose W somewhere, then you can interpret that as W square times X and then differentiate it the usual way. The question is, can this go wrong, that approach?
I think the rules that have been mentioned in the slides. Yeah, I can understand your point. It is good to have a cross check mentally when we are writing differentiation of complex expressions, just to be sure that the dimensions of this is proper or not. That is definitely
Okay.
we should do. Yeah.
Yes.
Okay. Let's go to the next question. The correct expression for updated mth weight in gradient descent algorithm is okay. So what we are doing is updating only one weight and its index is m. So Wm is equal to so first one is definitely not going to be there, and the last one, because they are adding something. So instead of going in towards the minima, we are actually going the towards the opposite direction. So these two are definitely wrong. The only possible options are the middle ones. And the third one has a missing parameter. Can anybody guess?
Alpha.
The learning rate.
No learning rate.
Yes, absolutely right. So, and therefore, this option is wrong because it is always moving. So there is no control on the step in the third equation. That's the meaning of it. And therefore, the correct answer should be B. Okay, now let's go to the fourth question. A learning curve is a graph between loss function and parameters of the model, loss function and the learning rate, loss function and number of iterations, loss function features of the model. Loss function, I think, and features of the model should be.
No, that learning rate.
Sure.
No, the
No, no, no,
number
no,
of
no.
iterations.
Iteration. Sorry, sir.
Right. Because if we type learning rate on x-axis, for as of now, in week 2, sir has taken constant learning rate. He has not talked about changing them during the training. So we are going to assume that the learning rate is constant during the training. So if we take learning rate on x-axis, that is not going to give us any meaningful plot. So that is out of question. The first one, loss function, the parameter of the model, that is also doesn't make sense. The only thing that makes sense is
That would be
option.
that would be the GeoGebra surface that we saw. That would be the graph. For the
Exactly. Absolutely. So, first one, there is no learning happening. I mean, it's a visualization for us to figure out how the loss function looks like, how the loss surface looks like, but there is no learning as of that. The third one, loss function versus the number of iterations, is the right answer, because we want to figure out as the number of iterations increase, what is happening to our loss function, whether it is going down, it is going up, or what is happening with it, or is it staying stable. So by that, we can actually figure out whether our model is learning or not. Because if it is going down, that means, yes, we are going in the right direction. Our loss is reducing. If it is staying exactly the same, that means there is no more learning to do, or there's something wrong with the model or the approach we are taking. And the third option is it could possibly increase. If that is happening, loss function is increasing with the number of iterations, that has a serious problem that we have to address. So the correct option should be loss function and number of iterations, because all these things can be learned, can be figured out by learning curve only. Okay, let's go to fifth part. So this one is about different variations of gradient descent. Okay, the first question is, we obtain smoothest learning curve for which of one of the following?
Batch gradient descent.
Okay,
What is
I
simple
think
gradient descent, by the way?
right. I think there is scope for confusion, because simple gradient descent and branch gradient descent, there is no clear demarcation. So the correct answer for this one should be the gradient descent, or it is also called batch gradient descent, in which before updating weight vector, we run through all data points. Okay, so that should be the answer. Stochastic is definitely not going to be the answer. I think batch should be there. Let's see.
I'm sorry, so why not simple?
Actually, they are synonymous. I'm not sure why simple is written there. It should be corrected. Maybe it should be mini batch, the second option, and then the third should be simple gradient descent.
If
But the
that
one
is the case, then simple would be the right answer, right? Mini batch is still more noisy than batch.
Batch.
Right?
Yes, absolutely right. Yes. Okay, let's go to the next question. Stochastic gradient descent is a special case of mini batch gradient descent with a batch size less than or equal to 5. What do you think of this?
No.
False. Yes.
False.
Exactly. Stochastic is a very specific variation of gradient descent in which the batch size is 1. So after reading through one sample, we update the weight vector right away. Okay. Question number 3. Which of the following has most erratic learning curve? Okay. So by erratic, it means it possibly goes away from the minima, or doesn't take the best option, but it does so more often than the other variations.
Stochastic.
For this one, there is no confusion, right? Maybe batch stands for mini batch. I have to check this one. Increasing the size of batch makes learning curve more erratic, learning curve smoother, learning curve asymptotic, no. So smoother, definitely. We can have so we have a spectrum, full batch gradient descent, in which we go through all samples before making updates. On the other hand, we have a stochastic gradient descent. We run through just one sample and make the updates. So as we increase the size of the batch, we definitely get a smoother curve. The reason for that is, as we increase the batch size, that batch is a better representative of the entire data, and therefore it is supposed to guide us towards the minima in better way. Okay, let's go take this question. Following table shows the value of actual and predicted labels. Find the root mean squared error. Okay, should we solve this one? Okay, let's solve this one. Okay, 1.5. So the values that we have is 1.5. Then we have 2.5. Sorry, 2.2, 3.5, 4.1, and the x values are 3 and 4. So in order to calculate the root mean squared error, so its formula is something like, anybody would like to say what the formula is?
Yeah, 1/2.
Okay.
Yeah.
Square root of?
No. Root mean square, I think 2/n, right? Because mean is there, 2/n. 2/n and then SSE. 2/n SSE with a root over sign. Yeah.
Something like this?
Yes.
Okay, I am not sure why 2 is over there.
Because SSE is 1/2, right? So then it will go cross.
I see.
The loss function is 1/2. SSE doesn't have 1.
Right. So something like this we can write. I is equal to, let's say, 1 to n. See.
Yeah, like y minus y predicted, y hat. Square.
Yes. right?
Yes.
Okay, so I think all we have to do is the actual value and the predicted value. We take it the difference, square it, then we take the sum divided by the number of samples and take a square root. So this should come out to be. So if we take the differences of all of these, this will come out to be 0.5. This will be 0.2. Again, this will be 0.5 and 0.1. I hope I have taken the right values. Can someone confirm this?
Yeah, this is correct.
Okay. So now all we have to do is we take square of all of this. So let me write this over here. This will come out to 0.25 plus 0.04 plus 0.25 plus 0.01. So this should be 0.55. Okay. And now what we do is we divide it with the number of samples, which is 4. So we'll get something like 0.1375 and take the square root of it. I think it should come out to be around 0.4 is 0.16, 0.3 is 0.09, something between 0.3 and 0.4. I think it should be the answer. Okay, so there is this only candidate I can think of 0.5, 0.48, 0.55. All of them are greater than 0.4. So I think this is the right answer. Okay, let's go to the next question. Consider the following steps, which are optimization, modeling, evaluation, data, and loss function. Correct sequence of steps involved in linear regression is. Okay, let's start with one by one. So which should go first? Data, which is 4, definitely. So first two options are out of question. The next step is
Model.
So this is also 2 in both of the options. The third step is
Data model.
Loss function.
right. Loss function, and after that there is optimization, and then there is evaluation, right? So only one option stands to be the correct one, which is the third one. And in general, also these 5 steps belong to any machine learning model, not just linear regression. Okay, let's go to the next set of activity questions. So this one is about data, how we explore it, how we work with it. So I think these are activity based questions. So I think the data set must be in the video itself. Can somebody help me with what is the shape of the data?
Yeah, 100 common. Yeah, first one.
First one. What is the shape of labels? I think they should be same, right?
100, yeah.
Yes. The third one is what is the ratio of training and test sets in the video?
20%, 0.20.
Okay, so 0.20, I think sir must have used trained test split.
Correct.
Correct. And in that the parameter was given 0.20.
Right.
Okay, so that stands for the test
80-20.
set will be 20%, right? And the training set will be 80%. So the first option should be correct. All right, let's go to the next question. Now this is an interesting one. Now we have started to see some code snippets. All right, which of the following is correct way to check if X, which represents feature matrix, and W, which represents parameter vector, can be multiplied? Okay, we want to multiply them and we want to figure out if they are compatible. Both of them are NumPy arrays. All right. So the first one, it says number of rows.
Third one, yeah.
Third one, the number of columns and number of rows in W. Exactly, I agree with. Okay, which of the following is correct way to predict X and W are NumPy arrays representing the feature matrix and weight vector respectively? Okay,
The first one.
the first one, right. And so third one is definitely why it's even there. It's definitely wrong because we are dividing two vectors and they are not divisible either. The last one we are multiplying with X with W.
Then again X.
And then again X. So I'm not sure. They don't even have the proper dimensions to do so. So that's wrong. Second one is also wrong for the same reason. And only option remains is the first one. So yes, X multiplied by W. Which method of inference is faster, vectorized or non-vectorized?
Vectorized.
Yes. So I think Shruti also asked something about this in previous live session in last week, in which she asked why it is faster than the non-vectorized version. So I think it is because of two reasons. One is that the routines written for NumPy are in optimized C language, and the second thing is the NumPy arrays are homogeneous.
Yeah, another thing, like if you use vectorized one, then you can use the GPU efficiently, right?
Right. So even if we remove GPU for a minute, even then vectorized versions are faster than non-vectorized versions. Okay. So on a side note, does anybody know if you want to, let's say, if we empirically want to calculate the time taken by vectorized and non-vectorized versions, how can we do that?
Percentile.
Percentile?
Percent time.
Percent time. Yes, that is right.
The
In
magic
Colab,
function.
yes, sir.
It's the IPython magic function. Is there some?
Absolutely right. Yes.
Yeah,
That's right. Yeah. Okay. Let's go to activity question 2.9. All right. So we have a code snippet. What you want to do is we want to figure out its output. Okay. We have X. It has 2 samples and 4 features. We have Y, 2 labels corresponding to 2 samples. We have W, which is 1, 2, 3, 4, a weight vector. A is the loss, and okay, A is the loss value that you want to calculate between X, W, and Y. So how we are going to do this?
So like X is a 2x1 matrix basically, and Y is like 2x1 again.
Right.
Yeah, then XY and W is given, right? XW, if we calculate, XW minus Y.
Okay.
That will be your loss, and then we need to find out like the numerical value.
Right. So XW minus Y is going to give us the loss values for individual samples.
Yes.
So it will be a vector. Right.
Correct.
And then to get the final loss value from this vector is, how can we do that?
That SSC, right? Or like SSC is that Sarah's taken. That means
Yes.
1 by 2 and like the norm of that vector.
The norm of the vector.
Loss vector, right? Loss is a vector.
Yes.
So 1 by 2 and multiplied by norm of that vector.
Okay. So just to be clear, what you want to do is, square the individual terms in that vector, right?
Correct. Yeah.
And then add them together.
Yes.
And then multiplied by half.
Half.
Right. Yes. So that is the answer we're going to get. I hope I can skip this one, or does anybody would like me to go through the calculations also? Okay. Then I think it's a straightforward set of calculations. Let's go to the next question, which is what is the value of A, which is the loss, if A is doubled? Sorry, W is doubled. So what will happen is XW minus Y, but this time what we'll do is 2 times XW minus Y and then calculate the loss.
Correct.
Okay. All right. Let's go to activity 2.10. Which of the following method? So this is about optimization. Which of the following method use pseudo inverse of matrix feature matrix? Okay, for this you have to go through the video very carefully. Okay, which one is that? I think predict is definitely not going to take the inverse. Add dummy is also not going to do anything. There are only two things, which is computation of loss. This is also not going to take the inverse of any matrix. Only thing which remains is normal equation. So if I remember correctly, this should be the answer.
So this normal equation, like Sarah has mentioned one, like in that optimization, you have two ways. One is normal equation, and another is this gradient descent, right?
Right.
So that normal equation you are talking about, right?
Yes, yes. That's the
Okay.
one.
Yeah. Yeah, because they are X transpose X inverse you need to calculate.
Yes, yes, absolutely. Okay, let's go to the next question. Which of the following statements will correctly initialize the weight vector? Okay, at this point of time, I think this should be something that we have gone through already. So if you want to predict, what we do is we multiply x with w. So the number of columns in x should be exactly equal to the number of rows in w. So number of columns in x could be obtained from x dot shape and
Yeah, the
passing
second
minus.
one.
Second one will give the number of rows.
No, actually, like okay. Yes.
This
Minus
should be
one.
right one, right?
Minus one, yeah.
Minus one. All right. Let's go to the next question. This is about evaluation, I think. So this is straight true or false. In the video, stochastic gradient descent doesn't reach minimum point in loss space eventually. Okay, so somebody can help me with this one. Does it reach the final value, the minimum value eventually or not?
It might not actually the stochastic gradient descent.
Right. So that's slightly okay. I take your point because with every
Here it's not asking for the exact loss, it's in the loss space, like it is getting nearer to the loss, so it would be true.
yeah, that's also right. So if we say that exactly minimum point of that loss space, it is possibly not true. Possibly again, but as the number of iterations go on, it'll meander around the minimum loss. So I think the intention of asking this question is that. So let's go with true and see if the answer is right. Or doesn't reach. It should be false. Is it true or false? In the video, mini batch gradient descent reaches minimum point in loss space eventually. I think this should be true. And say true or false, learning schedule gradually increases learning rate. So, as the learning, as the number of iterations increase with every iteration, do we want to increase our learning rate or decrease it or keep it constant?
Decrease.
Right, decrease is definitely one option. We can keep it constant also. But
Yes.
one thing that is absolutely wrong is increasing the learning rate.
Yeah.
So increasing learning rate is equivalent to taking larger steps, attempting to reach quickly to the minima. But in that process, you might actually overshoot our minima. So this is going to be wrong. Okay, so doesn't I think it should be true. It should be true. We'll have to check this one. The third one, learning schedule gradually increases learning rate. This is false. This is correct. I'll have to check out for question number 2. All right, let's go to question number activity 12. Which of the following functions in linear regression class is used for evaluation of performance? So this is also based on the
First one.
video.
Yeah,
Okay.
RMSE.
RMSE. All right. Learning schedule cannot be there. Fit cannot be there. We are measuring evaluation. Loss. Okay. I'm a bit confused between the two. I have to be very. I have to look at the video once more to be sure. RMSE is
Yeah,
the right one.
yeah,
In
that
video, it was like at loss, in the loss we are using SSC, and for RSME was using for evaluation.
evaluation.
Okay. Okay. That's actually right. RMSE should be there. Okay. Which of the following function in linear regression is used for calculating the gradient? I think if you look at the just names, this should be clear. RMC is definitely not for computing gradient. Learning schedule is definitely not. Fit is also not there. Compute gradient. This is the one. Okay. All right. Let's go to the next question, which is the a programming practice question. So before we move on, does anybody have any question so far?
Yeah, sir, on that like gradient descent, mini batch, and SGD. Okay. So here we are like say for example we are initializing this W vector with NP zeros, right?
Yes.
Okay. Now say for example like if our loss surface is something like which is very like a kind of a plateau, and then it is coming down. Okay. So then like and say for example your zeros are on the plateau side, right? So there like if you start like whatever it is like stochastic gradient descent or mini batch or anything, then you will get stuck in the plateau itself because not much gradient to update.
You're absolutely right. The gradient will be zero at a plateau.
Correct. Now the question is like is it like kind of in practice like say for example instead of initializing W as zeros and also like more we get close to the minima, okay, that time we need to slow down our learning rate, right? So first say for example do like some epochs with stochastic gradient descent or mini batch to get closer to that and use that W to start with a normal gradient descent.
That is actually a very good idea. Rajiv, is it right?
Yes.
Yes, Rajiv. So that could actually speed up your training process. So you can, so as you go on training your model, you with every iteration you can change the size of the batch.
Right.
So let's say the first round you go with a stochastic. In the next round you make the batch size to 2. In the next you make it 4, 8, or somehow progress gradually. And at the end you start, since you want the model to be very, very accurate. The last few iterations you can go with full batch gradient descent.
Okay, so and the last question is, say for example you have the training data. Okay, now from the training data, sorry.
Yes.
Okay, in the training data, if I do some kind of a binning operation, okay, and because the y value is continuous, like I'll do some kind of a binning operation, and if I say for example I find that there is a class imbalance, okay, so that means like some part of that bin is having very less number of features, okay, less number of samples in that particular bin. In that kind of situation, if I use like SGD, right, then it will be detrimental, right?
So what you're saying is the label is skewed. The distribution of label is skewed. It's not uniform, or
yeah, like that could be one thing, but yes, like that could be that is the thing. Your label is skewed, right?
Right. So Rajiv, that's a very practical problem, and that is definitely we are going to talk about in ML practices. So we have a solution for that also. So quickly, if I tell you, we are going to scale the target label also.
Okay, you are saying like you will be scaling the target level, and then or maybe like whatever is undersampling, oversampling, through that you will do a class balance, and then you will use SGD, right?
See, class balance problem is not directly applicable because the problem is regression, not classification. The class balance problem comes in when there is a set of classes in which we want to distribute our samples.
Correct. But say, for example, you have a regression problem. Okay.
Mhm.
And you have that y values. Okay. Now you do
Okay.
some kind of a binning. Now y is
Okay.
a real number. Okay.
Right.
Now if I do the binning and I see there are, like, say, for example, some beans are very less y.
Okay.
That means these data so this data, like, my fundamental assumption is that it is like a IID samples, probably that doesn't hold good, right? That point.
See, so no, we still assume that.
We'll
So
still
see,
assume.
yeah. For example, that let's say this is the distribution of your label and it is highly skewed. It is left skewed. Okay.
Correct. Yeah.
So if you try to create bins on it, so this is how it will look like, I think.
Yes. Yes.
Right.
Hmm.
So the number of samples around this peak, those bins are going to get higher number of values, and the remaining are going to get lesser. Okay. So if you run stochastic gradient descent, what is going to happen is for
So it will be very erratic, right?
I wouldn't say very erratic. It is going to be erratic anyways. But for these, so there is a set of set of values. You can see. I hope you can see in the circle. So these are large in number. Okay, so somewhere around here. So these values, the distribution or density of these numbers are larger. So your optimizer will be guided by these. So these values will force dominate the optimization procedure, since the number of others are not that great.
Okay, because see, the reason, like, I was thinking this. So for example, when you like for SGD, every level you will be updating, every sample you are going to update the W, right?
Yes.
Now before you come to like those dense areas in the diagram, right? You might have gone like far away from the original minima.
Possibly.
Okay.
I wouldn't say far away, but yeah, definitely some direction which is away from minima. So that is okay, right? Because we know that stochastic is not supposed to always point to the minima. It is supposed to reduce the amount of computation we have to do in order to reach to the minima.
Yes.
Right. So yeah, to achieve that goal, we allow stochastic gradient descent to make some mistakes and wander off in the wrong directions.
Okay.
All right. Okay, so let's go to this programming practice. Okay, before that, anybody would like to say something or have any questions?
Sir?
Yes.
The collab notebook used by the instructor, will it be shared with us?
No, they will not be shared. The sole purpose of doing that is to encourage students to write code.
Okay. Then this will not be the part of programming exam.
This will definitely be part of programming exam.
But he is using various libraries and functions from inside that. Would we have to memorize all these things?
See, I wouldn't say memorize them as in, if you write and practice them and observe their behavior, you will remember them.
Oh, okay.
So I would suggest you to do this. For practicing the programming, look at the videos that sir has created. Go through the code that he has written and type those code lines yourself. Type, do not copy from anywhere. Since you are learning it, so it's a good practice that those functions and APIs, then coding pattern goes into your memory. So if you do it once or twice, you will start remembering things. You wouldn't have to, nobody has to, I mean, you wouldn't have to remember or go to the documentation. You will remember the important functions.
Okay, thank you.
Yeah. Okay, for this question, write a function add 1 to x that includes first column which has all 1 in it. Okay, okay. So all we are doing is we are adding dummy feature into this. Okay, okay. So for this one, we can see that this np.column stack. So there are multiple ways to do this. Column stack is one function. So it is specifically designed to add columns. I mean, concatenate two matrices column wise. Okay. So X matrix, our input matrix is supposed to have multiple features, or it could possibly have multiple features for sure. And for this problem, I assume that it has. Okay, so it will have multiple features and has one or more number of rows. That is fine. So it's X has a shape of two-dimensional matrix. Right. Now, can anybody tell me about this one? What is the shape of this vector or matrix?
This is like x dot shape 0, basically rows, number of rows in x.
Right.
Okay. And then np1 means np1's x dot shape 0, that means like first column, and with number of rows whatever is there in x.
Right, absolutely right. So this is going to give you the right answer if you stack them column wise. So what will be the shape of this highlighted piece of code?
Okay, this is only that part, right?
Yes.
That is n cross 1 actually.
N cross 1 for sure.
But only that part, like np1's like x dot either n cross 1 or 1 cross n.
This
Okay,
will be
so
n cross, like it's just n vectors.
yes, yes. So to be specific, Rajiv, your answer is right. If you're talking about theoretical part, say what is the shape of this? All row vectors or column vectors, they always have a shape of 1 cross something or something cross 1. That is true. But when we are writing NumPy code, you have to be very careful about this. This highlighted piece of code has only one dimension, which is the number of rows. The second dimension, it is not even there. So if you copy this, the output of this highlighted code into a variable and see the shape of that variable, you will see some n cross n comma nothing. Okay, so just a side point to remember this. Sometimes, if you don't take care of the dimensions, we could get very wrong answers. Okay, okay. So let's go to the next question. Write a function multiply x comma w to multiply feature matrix x and the weight vector w after adding the dummy feature to the feature matrix. Okay, okay. So this builds upon the previous question. So before we do the multiplication, we have to add the dummy feature. Okay, so see the line number 7. It does exactly what we discussed in the previous question. It adds a column of ones right before x. And the next step, which is line number 8, we are trying to figure out if they are actually consistent or not. That means number of rows, number of columns and number of rows in x and w respectively, they are equal or not. If they are equal, that means they can be multiplied. Otherwise, we return none. that means the multiplication is not possible. Okay, let's take care of this third and last question. Write a function loss which has three parameters x, w, and y, which takes feature matrix x, weight vector w, output label vector y, and returns the sum of squared loss while implementing regression model. Okay, it says that do necessary pre-processing of x. I think it involves adding 1 to x and then calculating the loss.
Yes, if you do not add 1, then xw minus y will not work.
Xw
Minus y, because xw is basically w0 x0 included, right?
right. Yes, so that has to be included. So w in this one, which is this particular value, I hope you can see the highlighted part. It has the parameter for dummy feature also. That means you will have to add add a dummy feature in the feature matrix, which is being done over here, exactly like the first programming question. The second one is this time we are again we are trying to figure out if they are compatible to be multiplied. If they are, after adding the dummy feature, then what we do is we make the predictions. Okay, so this vector small e represents the predictions, not prediction, sorry,
Error.
I think there is something wrong. This is not the right answer.
We should subtract minus y from this.
Yeah, instead of
Yes,
equal
yes,
to
yes.
some, yeah, correct.
Right, now I think it should produce right answer, right? So predicted minus ground truth labels, this is going to give us the error vector, which will have error for individual samples. And after that, what we do is we take the transpose of this column vector and multiply it with itself. We are going to get a single scalar value and multiplying that by 0.5. Okay, so I think this should give the right answer.
Correct.
Sir, I have a question related to NumPy.
Sure.
What's the difference between, like we in this we are using np dot transpose, and what is the difference between e dot transpose and np dot transpose when we are passing the argument matrix?
I think they are same. They should be same because both of them return another copy of transposed matrix.
Yeah, they are same actually.
Yes.
Dot t and np dot transpose will the same thing.
Give exactly same value, right? So, does that answer your question? Hello? Hello? Okay.
I think he got
I hope
dropped.
that answers the question. Okay. I hope that that answers the question. Any further questions?
Hello, sir.
Yes.
So I have a question. It's not related to programming. Can I
Okay, go ahead.
Can you please clarify what is the difference between a class and a label?
Class and a label, right? So, in machine learning, you will see different type of variables. So one variable could be number of runs scored, one variable could be temperature, and average temperature of the day and things like that, which are numerical. The other things that we will see is the prominent examples for classes could be you have a picture and you want to figure out whether there is dog in it or cat in it. Okay.
Yes, sir.
Hello. So label is a generic term. It could stand for real numbers. It also could stand for classes. For classification problem, it stands for classes. For regression problem, it stands for real numbers.
Okay.
Okay, so label is a general term for supervised learning.
So basically, if I have
Yes.
a variable called runs,
Mhm.
if I have a variable called as temperature,
Mhm.
which is a continuous variable,
Okay.
in that case, all the values that will be taken by that variable will be labels.
All the values taken by that will be real numbers, and that column will be called if it is a target. I mean, we want to predict the temperatures, then it becomes label.
Okay. Okay. And
So
if
label is another name for target. You can say loosely.
okay, okay. So basically, the target is that output variable, output class, which has all the values as labels. Whatever
Yes.
value it's going to take, it's as labels, and the other input variables are called as classes in a loose way. Is that correct?
So other variables are called classes. What do you mean by that?
For example, if we want to predict temperature, then
Mhm.
the wind velocity, the humidity, all these will be used to predict the temperature as a model.
Okay.
Just a hypothetical example I'm giving.
Sure,
In
sure.
that case, the wind velocity and humidity are classes, and the temperature is the target variable which has all the values as labels. Is this
Okay.
correct?
Okay. I see your point. See, so the temperature is a label, target variable that is settled. The humidity and wind velocity, they are actually features.
Okay.
They are not called classes.
So what would be a class if we are going to add, giving this example, what would be a class in this example?
Okay, if you have gone through the video, sir has taken this example that we have a two-dimensional image, black and white. There is some digit written in it, and you want to figure out which digit is that, right?
Okay, yes, sir.
Do you recall that?
MNIST problem, right? Digit.
Yes, MNIST problem. Yes. So the possible output for every photograph of a digit are 0 to 9.
Yes, sir.
Yes.
Yes.
And the input feature actually that is going to come later in the course, but what you will do is you will have to let's say for now assume that there is the size of the input image is 10 by 10. So what you can do is you can unravel that entire matrix into a single column vector of 100.
Okay. Yes, sir.
And that becomes your feature vector.
Okay.
Okay. So now you have feature vector, and then you have the output that you want to predict, whether it is which digit is it, 0, 1, 2, 3, 4, or up to 9.
Yes, sir.
Right. So this 0 to 9 that you want to predict is the class.
Okay, 0 to 9 is the class. Okay.
Yes. And there could be some more. I mean, in this example, we have only feature vector of size 100, which is the picture of that digit.
Okay. Okay. So there is no label here.
So the label here is the predicted class.
Okay, label is the digit.
Digit, yes, 0 to 9. It could take any value.
And a specific value is a class here.
Yes,
Zero.
specific value is a class.
Okay, got it. Thank you, sir.
Okay. Okay, are there any questions?
So
All right.
one more follow-up. You mentioned
Sure.
unravel. So basically what you mean is you have an image is basically a pixel, like it's an array, it's a it's a matrix which has
Right.
all the pixel values. So
Yes.
if it is a 10 cross 10 matrix, a 10 cross 10 image that we have,
Mhm.
when you say you unravel it, you basically mean that it's going to be 100 vector of one single row, right?
Yes. So let's say we have 10 by 10 matrix. Every column we separate the 10 columns and put them one beneath the other.
Okay. Got it.
Okay, so this way we get all the pixel values in a single column.
Okay. Got it.
Yeah.
So you're going to associate and weight with each and every pixel here.
Exactly. So this is one way to pose the problem. There are other methods. There are other advanced methods also. For example, neural networks, in which you create features out of this image. But that's something else. For now, this addresses your question: what is label? What is and what is class?
Got it. So linear regression, can you give an example where it is used heavily?
Where it is used
Heavily, like day-to-day applications.
Day-to-day applications, of course, definitely. Yeah, so let me. So let's see if I want to see Chennai temperature. So it is going to give us this, nice line. You can see, right?
Yes.
So this is spread over multiple days. You can have a line if right now we are taking advantage of the service. We could also see with appropriate data what is the temperature throughout the day in 24 hours. So you can see you are going to get a smooth, maybe not very smooth, but this curve of real numbers.
Okay.
Right. And you can see, this has all real numbers. Of course, for sake of simplicity, this website is only printing the integral value of the temperature, but it could be anything 23.4 or 5 or something like that.
Okay. So this is where linear regression is used heavily.
Not linear regression. You asked me for regression, right?
Okay, regression. Okay. So which type of regression will be used in temperature? Like any idea?
So see, linear regression is one way to solve regression problems. There are other models also. Okay. Let me give you another example of a regression problem.
Okay. Stock market. Okay.
Yeah, stock market. Let's say we look at Sensex. See, in this one also you are able to see quite a curve, which is a set of which is plotted from a set of real numbers, and here you see decimal points also very clearly.
Yes, sir.
Right. So this is another example of a real value to be predicted.
Got it, sir. So they essentially use polynomial or more types of regression, linear variation of linear regression in a way somewhere.
Yes, definitely.
Okay, sir. Okay.
Sir, in this error, like whatever error we are calculating, so that is kind of a it is a variance measure, right? Like how much you have calculated some like mx plus c, and how the spread is, like what is the variance? Basically, essentially we are calculating the variance, right? Y spread minus y whole square, that is the variance.
Yes.
Correct?
Right.
Now as you have opened up that stock market stuff, right? So like is this variance that is good for okay, variance is one measure. Another measure is called volatility, right? Are they both the same?
See, so you're talking about a specific data set. I mean, a specific problem, which is stock market prediction, right?
Yeah, the time series data. Yes.
Yeah. So for that volatility, I'm not sure how it is defined.
Okay.
So there must be some formula. Is it a numeric value?
Sir, can I take it?
Yeah, sure.
Yes.
Yeah. So you are talking about beta basically, right? High beta stocks.
No, I am not telling anything. Like what I am trying to say is, like in these, like while predicting stock, that is also a regression problem, right? But here one common term that comes is volatility. But when I see that regression problem, they are like we generally measure the variance. Like error is nothing but the variance, right? Now, is that variance is equivalent to volatility, or volatility is something different? That was the question.
So in stock market prediction, when we say volatility, it is basically counted from the previous day price. So how much it has gone high or low. So that is nothing but variance of that particular day.
Okay, but volatility is still the variance measure, right? That's what.
Yeah. So for that particular day, it's a variance of that day. So if you take it over the several days, it becomes variance over several days.
Okay. So that means the data will be kind of like, say, for example, previous day minus current day. So now the variance on that is the volatility you are saying, right?
Yeah. So that particular day, it takes basis of the previous day's price.
Okay.
Sir, can I request the teaching assistants to find a data set or a competition on Kaggle which uses linear regression heavily, so that we can tingle around with it? Like, which one you would suggest? In the next session, we can
Okay.
have something.
Sure. We can definitely do this. I would request you to please post this request on Discourse also. I'll properly write answer to that so that everybody else also gets an idea about it.
Okay, sir. Thank you, sir.
Okay.
I think there is already a post actually on Kaggle stuff on Discourse forum.
Oh, is it? I think I'm not aware of that.
Okay, like either that is in MLT or MLP in some forum it is there, because I have seen that stuff.
May I ask a question here?
Sure.
Yeah. So in the lecture we discussed that there are two methodologies, right? One is the analytical method, other is this gradient descent, right? So analytical method directly calculates the inverse of the X transpose X matrix and determines the coefficients, right? So in case of gradient descent, what is the minimum number of training samples that are required in the practical setup for this in order for us to see these effects of convergence and the learning curves and realizing the exact learning rates, in order to actually see all these effects that we discussed in the lecture, the learning curves converging. So what is the minimum number of training samples? Because analytical, there is no such limit, right? Even 5, 6, like 7 training samples, like whatever it is, like it is just finding the inverse and finding the coefficients. But for the numerical thing, the gradient descent algorithm, what is the minimum number of training samples that are required?
I would say if you talk about number, if you want to observe all these curves and effects of learning rate and the things that sir mentions in the video, take around 50 to 100 points which are linear, almost linear, and they have a little loss between them. Okay, so this this one is not coming. Okay, this if you remember this particular example, the applet, interactive applet, it has been created exactly like that. So this set of blue points, I think they must be 50 to 100, something like that. But the minimum number of points, if you theoretically ask me, take any 3 non-collinear points, that should theoretically create should allow you to observe all those effects.
The gradient descent convergence, you're saying, with the 3 points?
Yes. 3 non-linear points, take them and try to fit a line between them.
Okay. But how does this have anything to do with the convergence of gradient descent? Having 3 lines simply means that you do a fit, but
right. But he's asking how do we observe those effects, right? So if you the minimum number of points you need is linear 3 points. Hello.
Yeah, sure.
So you know, all you want to do is, if you want to observe those effects, it's take something like this. If you can observe, are actually almost linear. There has been some this data set it's created. More details will be followed in this solve with instructor session that is going to come up on Friday. You in that one you'll do all those things practically.
All right. Yeah. Thanks.
Any other questions?
I'm fine.
Okay. So I think since there are no further questions, I think we need to close the session. And before closing the session, there's one heads up. So the next solve with instructor session that is coming up on ML techniques on Friday, it will be quite interesting because that will be very, very programming oriented. You will have problems in which you will have to write code to solve them. And that's how we are going to progress. And we will observe all those things that you just mentioned. The effect of learning rate, the trajectory of different variations of gradient descent, and so on.
Yeah, sure. I think we'll make sure that we are there.
Okay.
Yeah.
Okay.
Thank you.
Okay, sir. Thank you so much.
Okay. Thank you, everyone. You have been good
everyone.
support. Let's meet in the solve with instructor session.
Yeah.
Sure.
Bye, everyone.
Bye.
All right. Yeah.